Hello students, I hope you all are safe and sound. Okay, so we completed with Newton's first law and Newton's second law. Now today we are going to take up Newton's third law of motion. So here, as you can see, Newton's third law of motion is, the third law of motion states that for every action, there is an equal and opposite reaction that acts with the same momentum and opposite velocity. You understand the meaning of momentum, P is equal to mv, and opposite velocity also you understand. We have done these terms. So every action has equal and opposite reaction. Every action that occurs in this universe will have a reaction. Example, when you are pushing the wall will exert same, equal and opposite pressure, force on you, on your hands. So every action has equal and opposite reaction. We will be clear with this in our further slides. So let's move further. So the third law of motion states that for every action there is equal and opposite reaction. In other words, when an object exerts a force on the second object, the second one exerts a force on the first object that is equal and opposite in direction. Okay? Now, if there are two bodies, obviously the two bodies will be having mass. Mass is the amount of matter contained in the bodies. So if there are two bodies, one body is applying force on the another body. So another body has to apply force on the first body, which is equal in magnitude and opposite in direction. I hope the definition is clear to you. So let's move to some examples of Newton's third law. So as we can see here, Newton's third law, in the figure we can see F12 is equal to minus F21. 1, 2 is when the first body is applying force on the second body, and F21 when the second body is applying force on the first body. So force 1, 2 is equal to minus force 2, 1. It's written below also, FAB is force exerted by object A on B. So first one is the object which is applying force, and second one is the object on which the force has been applied. Okay, so things are very clear now. So we move to some examples. Let's see it. So this figure shows a balloon which was filled with air, and now the air has been released from the balloon. So the action is air rushes down. So air is coming out of the balloon, and what is the reaction? Reaction is that the balloon starts moving up. As the air is coming out of the balloon, the reaction is that the balloon starts moving in upward direction. So this is the action reaction which we have generally noticed in when we are preparing for birthday parties. We have seen this, that when a balloon happens to burst or something, so it moves upward. Okay, so let's see the another one. Now in this figure we can see there is a swimmer, and what is the interest of the swimmer? To move forward. So in that case, when she wants to move forward, so she is applying a force on the wall which is there. So when she is applying a force on the wall towards the right, the wall is applying equal and opposite force on the swimmer, and therefore the swimmer moves in the opposite direction towards which she wants. So this is the action and reaction example. We see further. Now in this, the picture is very clear. The action is that the man is exerting force on the rock. He wants to displace the rock, so he's exerting force on the rock. And what is the reaction of the rock? Reaction of the rock is also exerting equal and opposite force on the man. Okay. Now, if you look towards the foot of the man, action is man exerts force on the ground as he wants to push, so he is also exerting the force on the ground. And what is the reaction? Ground exerts equal and opposite force on the man. So this was one more a very good example of action reaction, which is following Newton's third law. So we move further. Now, we all have seen this, we all have experienced this some or the other time in our life. When we are there on the boat, the person who is moving the boat always rows the boat in an opposite direction in which we have to move. So he is doing an action that he is rowing the oar in opposite direction, and what is the reaction? The boat is moving in the opposite direction in which he is doing the action. So this is a very good example of action and reaction following the Newton's third law. So these were the few examples, and now the things are clear that what is Newton's third law? Every action has equal and opposite reaction. Okay. Now we move further to Newton's other law, which is other than the three laws. Let's see it. Now, other than the three laws of Newton, Newton's first law, second law, and third law, Newton also proposed a law which is known as Universal Law of Gravitation or Newton's Law of Gravitation. And what does this law say? Two bodies which have masses. Suppose the first body is having mass m1 and the next body is having mass m2. So these bodies will have a force which applies, mass m1 will apply a force on mass m2 and mass m2 will apply force on mass m1 according to their masses, and this force is a attraction force. This force is a kind of attraction force. Okay, and this was named as Universal Law of Gravitation or Newton's Law of Universal Gravitation. Okay, so let's see what does the law say. The law says every object in the universe attracts every other object with a force directed along the line of centers of the two objects. Now, whatever the masses we have, the force will be applied from the center of gravity of those masses, and therefore it's written about the center for the two objects. That is proportional to the product of their masses. The force is proportional to the product of the masses, and the force is inversely proportional to the square of the distance between the objects. Now, if Fg is the gravitational force, m1 and m2 are the masses of the two objects, r is the distance of the objects from their centers, that is the straight line drawn from the centers, that is the distance r, and g is the universal gravitational constant. Now, what is gravitational constant? We will learn over here. See to the side figure. Now, according to the law, the first part of the law says that F is directly proportional to the product of the masses. That means F is directly proportional to M1 multiplied by M2. Okay, now directly proportional, you understand by now that when the product of the masses will increase, the force will also increase. When the product of the masses will decrease, force will also decrease. So this is directly proportional. So force is directly proportional to product of masses, that is M1 multiplied by M2. Then the next part of the law says that F is inversely proportional to square of the distance between the masses. So let the distance be r from the centers. So F is inversely proportional to square of the distance. So F is inversely proportional to r square, and that is why it's written 1 by r square. Now if we combine both the equations, that means F is directly proportional to m1 multiplied by m2 divided by r square. Now proportionality sign has to be changed to equal to sign, because at times we have to put it in an equation and we have to find out the value of F. So we need to have a proportionality constant in order to equate the equation, and hence we have F is equal to G m1 m2 by r square. Here G is the proportionality constant which has equated this equation. Okay, so G is the proportionality constant and it has a constant value which we will calculate further. Okay, so let's move further. So as I said, that the force applied between the two masses will be F equals to G m1 m2 by r square. So here, for an example, I have taken the two masses as Sun and Earth. Now you can see the distance, that is from the center of the Sun to the center of the Earth, that is showing distance r. We have the force F1 which has been applied by Sun and force F2 which has been applied from Earth. Now, both these bodies will have a attraction force because they have masses. Now, what will be the force? Force F1 will be equal to force F2, and that will be G. M is the mass of Sun and small m is the mass of Earth. So, G M multiplied by M by R square. Okay, so I think you have understood the formula. So let's see further the unit of universal gravitational constant and the value. Okay, so let's move further. So the value of the proportionality constant G has been given as 6.67 into 10 to the power minus 11. And unit you can calculate if you take everything to the other side, leaving G to one side. That means F into R square by M1 into M2. So the unit of G will be F M1 F into R square, that is Newton into meter square, divided by M1 and M2, so divided by kg square. So the unit is Newton meter square by kg square. So F is equal to G m1 m2 by r square, where value of G is 6.67 into 10 to the power minus 11 Newton meter square kg square per kg square. Now, gravitational force is a very weak force. How? We will study in the further slides. Now, here we have some important points to remember. Now, if it is important to note that gravitational force between two masses is always attractive. So any two masses present on this earth or in the universe, the force acting between the two masses will always be attractive. Second, the force is directly proportional to product of the masses. Third, it is inversely proportional to the square of separation between the bodies, that is inversely proportional to 1 by r square, that is r square. Fourth, force is significant between two heavenly bodies. That means universal gravitational force is significant between two heavenly bodies, not between two bodies which are here on earth, but it is insignificant between ordinary bodies because of very small magnitude of G. When it will be calculated, it will be very small, and hence the force acting between very common objects will be very, very small, and hence universal gravitational constant will be too less to be experienced. It is experienced only between heavenly bodies. Okay, so we move further. Okay, so now we have force due to gravity. So what is the force applied by gravity. What is the force applied by gravity? So let's see. F will have the same formula. F is equal to G m1 m2 by r square. Let's take the mass of the object be 1 kg. Any object which is kept on surface of earth, let the mass be 1 kg. Now, capital M, that is the mass of the earth, let it be 6 into 10 to the power 24 kgs. It is 5 point something, and which has been approximated as 6 into 10 to the power 24 kgs. The distance between the center of the earth and center of the object will be 6.4 into 10 to the power 6 meters. And value of G we know 6.67 into 10 to the power minus 11 Newton meter square by kg square. So let us substitute all the values. When we calculate all this, we'll get F is equal to 9.8 Newton. Now, every object on the surface of Earth applies a force on an object which is moving away from Earth. That is 9.8 newtons. Force is 9.8 Newton. So, you know that acceleration due to gravity is 9.8 meter per second square. Now, force applied by Earth on the object is 9.8 Newton. The same force is applied by the object which is away from the Earth, but Earth can pull the object towards its center, but the object cannot pull Earth towards itself because the mass of Earth is very, very, very big as compared to the mass of the object. So here the body which is having a greater mass will be pulled towards the other. So as Earth is having more mass, so Earth is pulling the body towards itself, not the object is pulling the Earth towards itself. So I think the point is clear to you. So force applied due to gravity is 9.8 newtons. So we move further. So here we have relationship between small g and capital G. What is small g? Small g is acceleration due to gravity, and capital G is universal gravitational constant. Now, small g is coming from the formula F is equal to mg. We know that F is equal to ma, and in case of acceleration due to gravity, F is equal to mg. Now, according to universal law of gravitation, F is equal to G capital M small m by r square, because we are having capital M as the mass of Earth and small m as the mass of the object. Okay, now from equation 1 and 2 we equate both the forces. Force is equal in both the cases. So mg is equal to G mm by r square. So on calculation, m and m will cancel, small m and small m will cancel, and we have G is equal to capital G mass of the Earth by the square of distance between the two masses. So small g is equal to G m by r square. So it's very clear now what is the relationship between small g and capital G. We'll keep this in mind. Let's move further. Now here I have taken some points to make the difference between small g and capital G very clear. So we take the first point. An acceleration produced on a freely falling body due to the gravitational force on Earth is known as acceleration due to gravity. And what is capital G? Gravitational constant G is numerically equal to the force of gravitation that exists between two bodies of unit mass kept at unit distance from each other. So if you put all the values as 1, so G will be equal to the force over there. Okay. Second point, value of G near Earth's surface is 9.8 meter per second square. It may vary from place to place. So if you are towards the center of the Earth, it will be something else. If you are near the poles, it will be something else. So it varies from place to place. the value of capital G is constant because that is a universal gravitational constant, that is a proportionality constant. So it cannot vary, it has to be same, and that is a constant value. Now, small g depends upon the distance between the masses. Obviously, acceleration due to gravity will be the force by which the earth pulls a body towards its center. The force will be more if the body is far, and force will be less if the body is coming closer. Okay. Capital G is independent of the distance between the masses. The proportionality constant G, the universal proportionality constant, is independent of the masses. The force depends on the masses, but the gravitational constant doesn't depend on the masses. SI unit is meter per second square, and here the SI unit is Newton meter square per kg square. So I think the difference is very clear now. You have understood the difference between small g and capital G. Small g is acceleration due to gravity, and capital G is universal gravitational constant. So let's move further. Now, we have studied about equations of motion in our last turn. Now, if the body is coming towards the earth, if a body is coming towards the earth, then the equations of motion will be V is equal to U plus GT. Now, why G? Because body is coming towards the center of the earth. So here acceleration is G. V, you know, is the final velocity, U is the initial velocity, T is the time interval, and H is the height from the Earth's surface. Okay, so the first equation of motion when the body is coming towards the Earth is V is equal to U plus GT, H is equal to UT plus half GT square, and V square is equal to U square plus 2GH. Now, next case, when the body is going away from the earth, when the body is leaving the earth's surface, in that case, V is equal to U minus GT. Gravitation is in the opposite direction. Acceleration due to gravity is in the opposite direction, and hence V is equal to U minus GT. H is equal to UT minus half GT square, and V square is equal to U square minus 2GH. So wherever we have G, G is replaced by minus G. Okay. Now when the body is having a free fall, that means the initial velocity of the body was 0, and now the body has started falling freely towards the center of the earth. So in that case, if V is equal to U is equal to 0, so V is equal to GT, H is equal to half GT square, V is 0, U is 0, and V square is equal to 2GH, U is 0. So in these are the equations of motion which will be applied in these different cases. So whenever you are solving a numerical, you have to keep in mind that when is the body going above, that means leaving the surface, when the body is coming towards the earth, and when the body is having a free fall. So which equation to apply directly. Okay, so let's move further. Now this is a very easy term which we have studied from class 6 till now. So let's revise it. Mass. What is mass? Mass is the amount of matter contained in a body. Or in other words, we can say it is the amount of inertia of the object. That means unless and until an external force is applied to it, there is an inertia in the body which acts. So it is the amount of inertia of an object. Can also say mass characterizes the amount of matter contained in a body or in the object. Symbol for mass usually is M. Unit of mass is kilogram, SI unit. We always talk about the SI unit. So unit of mass is kilogram. Now, as we have that A is directly proportional to F, so we experimentally say acceleration is equal to force upon mass, because we know force is equal to acceleration into mass. So A is equal to F by M. So we know how to apply the formula. We know these formulae. So we move to the other part of this, that is weight. Now let's see what we have in weight. Now, weight is the force that results from acceleration by gravity on the mass of the object. So we know that weight is a force and force is equal to mg. So W is equal to mg. Let W be the weight of the object. So W is equal to mg. Whatever is the mass in that object into acceleration due to gravity is the weight. In modern scientific usage, weight and masses are fundamentally different quantities. So whenever we speak in physics, when we talk about physics, mass and weight are two different quantities. Why? Mass is the amount of matter contained in the body, whereas the weight is mass into the gravitational pull. Now, mass is an intrinsic property of matter, whereas weight is the force that results from the action of gravity on matter. It measures how strongly the force of gravity pulls the matter. Okay, so let's move further. Okay, so now here we have some differences between mass and weight, which you have already studied in your lower classes. Very fast, we'll revise this. Mass, the quantity of matter in a body is called mass. Weight is the force by which the earth attracts the body towards its center. Mass is a scalar quantity. Weight is a vector quantity. Why? To define weight, we have to see in which direction is acceleration due to gravity acting. So that it is a vector quantity. Mass of a body is constant everywhere in the universe. Whereas weight will differ because acceleration due to gravity will differ. If acceleration due to gravity is 0, so weight is 0, whereas mass cannot be 0. Okay. Mass of a moving body is m is equal to F by A, whereas weight of a body is equal to W is equal to mg. Now, mass can be determined by any ordinary balance, whereas weight can be measured by spring balance. SI unit of mass is kilogram, whereas unit of weight in a system is Newton. Okay. So this was all about the chapter. We'll learn about the units of weight and then we come to the end of the chapter. So let's see it. Okay, so finally we are on gravitational units of force. Now, MKS system, we have the unit of gravitational force as kgf. That means 1 kilogram force is the force due to gravity on mass of 1 kg. So what will be the weight? Weight is the mass, weight is the force on mass of 1 kg. So 1 kgf is force due to gravity on mass of 1 kg. So that means mass of 1 kg multiplied by acceleration due to gravity g meter per second square and therefore g Newton. So 1 kgf is equal to 1 Newton. Okay. 1 kgf can be equated as equal to 1 Newton. 1 kgf is 1 Newton force. Okay. Now in CGS system, it is gram force. 1 gram force is the force due to gravity on mass of 1 gram. So 1 gram force is equal to 980 dynes. And 1 kgf is equal to 1000 gf. When kg is converted to grams, it is 1 kg is equal to 1000 grams and therefore 1 kgf is equal to 1000 gram force. Okay. So this was all about the chapter. So on the next turn, we'll be taking up some numericals. So I will advise you people to please go through the book. Please read whatever is given so that the things are more clear to you people. I have tried to take up everything, whatever is given over there, but still you have to read each and every line of the book so that the thing is all clear to you people and you are perfect in the matter. Okay. So if you have any queries, please ask me in the comments below. So that is all. Let's take leave. Thank you so much. God bless you.